Good afternoon. Please identify with your full name, please. Good evening. Hello. Hello to everyone.
Salut Jean-François. È un studente di Pero.
He was in some other mini course.
Yes.
Hello.
So I've just realized that he was muted. So
Yes.
hello, Ricardo.
Hello. Sometimes people come out of the screen and come here, you know. Was on the other side, and
Yes.
now he's here.
Yeah, maybe it can happen also to him.
Oh yes, yes. Very welcome.
So come stai, Riccardo?
Bene, bene.
Ah,
Sta imparando l'italiano,
Ah.
sì, sì.
very
Un po'.
molto bene. Okay, so we wait just 5 minutes for the other to arrive. There is the usual Brazilian Italian delay.
Well, it's a very nice idea to have this meeting. So very nice.
Yes, yes, we can join forces with people around the world. It's very nice.
And also Lorenzo will do one in December, machine learning.
Machine learning, okay.
Yes, and there will be another in between network and centrality from Cynthia, from another state. It's in Brazil, but it's not still here. So, you know, will be a network semester. Okay, so welcome to everyone. It's a pleasure to have Riccardo Moolo from Italian, but from Belgium, visiting us here in Rio for a period of 1.5 months. So we hope to see you all in the near future. So Riccardo is currently working with Timoteo Carletti on problem of graph, hypergraph, topology of networks. So it will be a great pleasure to have this mini course from him today. Please, Riccardo.
Thank you, Professor Boastro. Thank you all for coming. So again, first of all, thank you to the professor for organizing this and for hosting me in her group. And also thanks to my supervisor, it's thanks to their collaboration that I'm able to be here, and also the Royal Academy and the FNRS of Belgium, who are funding my my staying. I will first thing I will give this course on the board. So for you online, someone else wants to be unmuted. I did unmute. Oh, okay. So if I don't speak loud enough, or if you don't see any question because I write too little, or I'm standing in the way too long, just don't hesitate to write it in the chat. So the professor will take care of it, and they will tell me, so I will repeat or rewrite what I need to, what I wanted to say. And then also, as I believe this will stay on YouTube, right? Yes. So please, if I make a mistake, let me know, also you in the audience. So I mean, I don't have the right to oblivion. I don't have the privilege of oblivion, so let me know. Okay, so the topic of this mini course is Turing instability. So you probably all know Alan Turing for his works on computer science. He's considered the father of modern computer. He's a war hero, as he helped decrypted the Nazi code during World War II. But he was born in 1912 and died in 1954. And his story is very interesting and also tragic. So I encourage you to check it out. So in 1952, so 2 years before dying, he published a paper in the framework of mathematical biology. So the issue was morphogenesis, which is the branch of developmental biology whose objective is to determine how the embryo is formed. Because at that time, one of the main issues, well, there were, as today, many scientific issues, but one of the main issues was to give account for this self-organization that we observe in natural system and also in artificial engineering systems. So we see patterns, we see emergence of collective behaviors, like in the flocking of birds or synchronization of fireflies. And one example was the formation of the embryo. So the question was, how is it possible that, so for active matter, like flocking of birds, that's another issue. But for inactive matter, so chemical reaction, how is it possible that they self-organize and they exhibit order? And so, well, of course, there was statistical mechanics that gave many examples of this emergent behavior, but then Turing had an idea, and with a simple mathematical model, he was able to prove that actually it was possible to have self-organization. So Turing mechanism takes a system of two species two chemical species. Then it goes beyond that, but it started with chemistry. And these species are in a homogeneous, stable equilibrium. Okay, so the system is in a stable, homogeneous state. And then the thing that is very interesting, and we will see with the details, is that after a perturbation, the diffusion is responsible for an instability that drives the system away from the homogeneous equilibrium and have patterns. So I find this extremely interesting because usually diffusion is what stabilizes a system, what homogenizes, but in this case is responsible for an inhomogeneous state. So this is very counterintuitive, but that's what Turing proved mathematically. And so before going to the mathematical details, just an intuitive description of the mechanism. So we have two chemical species. This is the formulation of Gerhard and Meinhard of 1972. So this was a later interpretation. So all these results were already there, but Turing didn't yet give this interpretation. So one species is an activator. Okay, so it self-activates and also activates the other species. So activates the reaction. So the first one is an activator, and the other one is an inhibitor. So it inhibits itself, and it also inhibits the activator. Okay. So, for example, if you think of not on chemical reaction, but on prey and predator. Okay, we have that the activator of the reaction is the prey, because can assume that they self-activate. They just need plants, grass to reproduce. And they also activate the inhibitor, because the inhibitor can eat the prey and so grow. But that the inhibitor inhibits itself, because without the prey, it dies. And then also inhibits the activator, because it controls the population of the prey. So this is the intuition behind it. And then again, Gerhard and Meinhard, they noticed that actually the diffusion that is responsible for this mechanism has to be asymmetric. So the activator has to diffuse slower than the inhibitor. So this is the diffusion in a domain. Sorry. So diffusion. And the inhibitor has to diffuse way faster. So today, I will go through the basics of Turing theory, not too formal, but yeah, I will point you to more formal references for those of you who are interested. And then next time we will see instability on networks, which will be the main topic of this mini course. And then next time I also will tell you how I will proceed next week. Okay, so we are talking about reaction diffusion system. I believe that someone does not have the mic on. Mic off. Yes, okay. Okay. And those were the equations studied by Turing. So let's start with getting to the equation that Turing studied. Okay, so we start with the law of mass action that says that the rate of a chemical reaction is proportional to the molecular concentration. So if we have a certain concentration, depending on time, we have that this concentration varies with a certain law that depends on the concentration itself. Okay. So with F nonlinear, otherwise it's not too interesting and also not very relevant physically because it diverges or it goes to zero. And then we can see that there's no space. So this is just, let's say, a well-stirred homogeneous domain. So the concentration depends only on time. In every point of a certain domain, we have the same concentration, which varies according to a law. Now, if we add space, so we consider a domain omega, open subset non-empty over Rn. So for simplicity, we will just take a volume of R3 bounded by an orientable surface sigma whose normal is n hat. Okay. Now in this domain, we can write the continuity equation. So we have the total concentration of so this U, I will try to write as good as possible, that for those who know me, you know, it's very difficult. So U, depending on X and T in the volume. We want to see how this concentration varies in time. And from the continuity equation, we have that this is equal to minus the flux from the surface. So we have the normal, the scalar product between the normal and the flux J. So this is the transport term. And then we have what is called, so again, on the volume, the source term. Okay, so we have the total variation of the concentration is the volume in the volume is given of how much substance enters or goes out or exits the surface bound the domain, and then what happens inside the domain. So what happens to the species, how the species is produced or degraded. And so now I have to delete every time. So then let me know if you need me to rewrite something, because yeah, I only have one board. One assumption that I will make now, and we stand for all the mini course, and if I forget to say it again, it will always stand, is that all the functions have the good properties of regularity. So you can exchange the integral and derivative and etc. So we can, first of all, we can apply the divergence theorem to the integral on surface. And then we can bring the derivative inside the integral. So we have that what happens in the volume is described by so the variation of U in time. Okay, then here we have the divergence theorem. So this is equal to minus the integral on the volume of the divergence of the transport in the volume. So if we bring it on the other side, we have the divergence of the current, sorry. Minus the function describing the dynamics. And then all integral equals 0. So now the volume is arbitrary. So this equation is valid not only globally in the volume, but also locally. Okay, so we can rewrite. so derivative of the concentration, we can bring everything again on the other side. We have fu of xt, and then minus the divergence on the current. And now we are almost there. To give a form of the current, we use Fick's law. So, okay, I will write here. You should see, yes, Fick's law of diffusion that gives an explicit form of the current. So the current is equal to minus a certain coefficient d of u that is called the diffusivity. It's a positive, positive constant that depends on the species, times the gradient of u. No, only one parenthesis, sorry. Okay. So now, if we plug the expression of J, we are done. We have our reaction diffusion equation. F of u x and t plus diffusion coefficient. So this is a d du. So the divergence of the gradients is the nabla square, so the Laplacian of u x t. Yeah, so this is the equation of a species in a certain domain on a concentration of u. So the variation of the concentration of a substance in a given. So this is of course valid also globally, but also this is valid locally, so also globally. Is given by how this certain substance is produced or degraded, so how this substance evolved, and how it diffuses in a certain domain. Okay, and so we see from the Laplacian that this problem depends on the geometry that we have. Okay, so today I will work with this equation. So Turing started from a system of two species. Okay, so we have species 1, U, activator, and species V, inhibitor. And we can write the equations. The T I will omit the dependence on space, and time is equal to a certain function f. Now f will depend on both variables, on both concentration, u and v, plus du nabla squared u, and then the equation for species v with now another function g, diffusion coefficient of species v, and then Laplacian of v. Okay, so we have two species in a certain domain. Again, an open subset of Rn. In this domain, we have these two species that they interact with each other locally. So point by point, they have a certain dynamics that is nonlinear. And then they diffuse in the domain. And usually, these systems are studied with von Neumann conditions. So the no flux. So the normal to the surface. Okay, so we have that sigma is a surface bound, regular orientable surface bounding omega, whose normal is n. And so we have the zero flux condition. So the scalar product between the normal and the gradients of U is 0, and the same of V. And this is the system studied by Turing, except for the names activator and inhibitor that were interpreted after. And so from here, we could take many different roads. There is a more rigorous discussion based on PDEs. I will not go to that. And then also the book of Murray, Mathematical Biology, solves it in a more rigorous way. I put the chapter in the Dropbox. So if you're interested to this, you can. There are lots of things that are still done in this field. Depending on the form of F and G, you have interesting things regarding existence and unicity of solutions. You have different geometries. You can actually study more realistic models. So I will not take this road, also because I don't know much of PDEs. I will study a much simpler system. I will study a one-dimensional system with periodic boundary conditions. So basically, the domain is a ring. Because, well, it's simpler. And also, I don't know PDEs, so. And then also because from this, it's much easier to move to networks, as you will see next time or maybe at the end of today. Okay, so I will not rewrite everything, but now the system is basically the same as before, but instead of the operator nabla, I can simply write the second spatial derivative for both species. Sorry, x squared. And then, so the periodic conditions. So U of x plus L, where L is the length of the ring, T is equal to U x T, and the same for V. And then also their derivative, their special derivative, U x plus L T x, and the same for V. Okay, now finally we can get to Turing theory. Okay, so this is the system that we are studying. You can already see, just a spoiler for next time, okay, that if we go from this to a network, to a 1D lattice, we already have a one-dimensional system with periodic boundary conditions. Okay, so I will delete everything except the reaction diffusion system. So for Turing theory, we need a stable, homogeneous equilibrium. That's the first thing that we need. So let us take a homogeneous solution, U and V. So for every point in the domain, we have the same concentration of species U and species V. This means that the spatial derivatives are 0, and also the temporal derivative, and that for both species. Then we need this to be an equilibrium point. So we assume that for both functions, this is an equilibrium point. So we have a homogeneous equilibrium. Now we need to impose the stability. So we can linearize by, so we can consider the linear system associated to the nonlinear system on this equilibrium by considering the Jacobian matrix, which is FU, FV, GU, GV, where FU, and that the same for the other three, is the derivative of F with respect to U calculated in the homogeneous, so in the equilibrium point. And so now we have a linear system, the linearized version of the system in case of homogeneous equilibrium. We have U, V, derivative, is equal to J0 Jacobian matrix, U, V. And so now we know that the equilibrium point, unless a pathological case that we don't have, of this linearized system is valid also for the nonlinear system for the Hartmann-Grobman theorem, at least locally. So we are sure that what we find for this is also valid for this. And we have stability. This linear system is stable if the trace is negative and the determinant of the matrix is positive. Okay, so linear stability. So the conditions for, so the first thing we need for Turing instability to have we need a stable homogeneous equilibrium. This is obtained if FU plus GV is negative and if FU times GV minus FV GU positive. Okay, first and second condition. Okay, now we are in a stable homogeneous equilibrium. How do we activate diffusion? We need to perturb the system in a neighborhood of this homogeneous equilibrium with a small perturbation, and this perturbation needs to be inhomogeneous, because if we perturb with an homogeneous perturbation, again, we have that the spatial derivative is 0. So I hope I'm not going too slow. Now we have a perturbation delta U that now depends on space. Sorry. So now our U of xt is equal to U star, the homogeneous state, plus a small perturbation, which depends on space. So it's different in every point. And the same for V. So in this way, we say that we activate the diffusion that was silent because there was no gradient of concentration. So there was no diffusion. So now, if we plug this into the system, we obtain that the derivative, spatial derivative, is still 0 for U star and V star, but not for the perturbation. And the same for the space. So the time derivative and the space derivative. And then F and G, I will do it for F, then for G is the same. We can write F of U star plus delta U, V star plus delta V. We can linearly expand at the first order with respect to both variables, because the functions are differentiable, regular. Of course, then it's interesting to see what happens if the functions are not regular, but this is another line of research. So we have F of U star V star. And then we have the derivative of F with respect to U calculated in U star. So that's exactly Fu, as we wrote before, times delta U. And then the same for the variable V times delta V. But this is 0 because U star V star was an equilibrium point. Okay, and then the same for G. So now we can rewrite the same system, reaction diffusion system, now for the perturbation in the linear regime. Okay, so this is valid as long as T is very small. But then it's enough because we want to see what happens near the equilibrium point. So then when we go away, it's not that we don't care, but we cannot anything. Okay, sorry, there was someone who was not muted. We can see it numerically. We cannot do much. So we rewrite the system now for the evolution of the perturbation. So we have derivative, time derivative of delta U is equal, if I'm not writing big enough, just write it in the chat. Delta T, so derivative with respect to time of delta U, Fu delta U plus Fv delta V, plus the diffusion coefficient is the same because we are still talking about species U. And then the second space derivative of delta U. And then the same for delta V. Now we have the function G. So G U delta U plus G V delta V plus the V second space derivative delta V, where Fu, Fv, Gu, Gv are those who satisfy this condition. Now, still, as I told you, I don't know PDEs, so I don't like this system. Still, I'm not happy because to solve it, we need PDEs. Is there a way to make it even simpler so that even I can solve it? Yes, actually, there are two ways, probably more. So one is more elegant, and we will see it next time, so Thursday, for networks. And otherwise, you can find it on the book Mathematical Biology. That is to develop, to expand the perturbation on the eigenbasis of the Laplacian. I prefer another way. It's even cooler, I think, because we can use the Fourier transform and so work in the space instead of x in the space of k, that is the wave number. And then things in that space are much simpler. So because we use a particular property of the Fourier transform, so the Fourier transform of the nth derivative of a function of x, the Fourier transform sends the function of f in the space of k, the wave number. This is ik to the n power of the Fourier transform of the function. Sorry, I will rewrite it bigger. Of the Fourier transform of the function, still function of k. So we see with this, we get rid of the derivative. So now, if we take the Fourier transform of this system and we send it into the space of the wave number, we have a much simpler problem. And we have time derivative of delta uk, meaning that the perturbation is in the space of the wave number, is equal to fu delta uk plus fv delta vk. And now we have a second derivative, so it's ik squared, so minus k squared, du delta uk. And then for v, delta vk derivative, gu delta uk, and then gv delta vk minus k squared dv delta vk. So now from PDEs we have ODEs. And actually we can write this in a more compact form. What's the variable I've used? Because then I need other variables. Yeah, so if I call Greek z, k, the vector of delta uk and delta vk, I can now write zk derivative is equal to jk zk, where now jk is J0, the matrix I already know everything about, minus k squared, and the diagonal matrix of the diffusion coefficient. Okay, so I studied a simple case of one-dimensional domain, but then from a PDE, I now have a linear system in the Fourier space, but then for what happens in the neighborhood of the equilibrium point, we don't care. We just care to see if the perturbation destabilizes the equilibrium or not. So if after perturbation the system goes away from the equilibrium or goes back. And for this, I can use the same technique I used before. So linear stability analysis. So the stability of linear systems. So we know that the trace of J0 is negative and its determinant is positive. I have an homogeneous equilibrium, homogeneous stable equilibrium. Now I want to see if with the perturbation I can have instability. So if the perturbation can drive the system away, so I need JK to be an unstable matrix. And actually, this instability is called Turing instability. So we can see already that the trace of JK is negative, because the trace of J0 is negative, and here I have minus something that is positive. Okay. So the only way to make this system unstable is to have determinant negative, because it would be in this case with trace. So I already know that the trace is negative. It would be a saddle point. And also what is interesting is that without a wave number, so if k is equal to 0, we don't have the perturbation, we have the system without space, so the isolated system, completely homogeneous, if k is 0. Okay, so what we need is to find this. We need to impose that for some case, the maximum of the real part of lambda 1 is positive. So the two lambdas are a solution of the equation lambda squared minus trace of jk lambda plus determinant of jk equals 0. I don't know how much time I have left. No, I will not do all the calculations. I have until 20 minutes. Okay, then yeah, then I can do it. So we need to find the two lambdas. Okay, assuming that we all remember this, then of course I will need something during the calculations that I'm now deleting. So
they're the real parts of the eigenvalue will be positive.
yes, at least one. No, I cannot have both because it's a saddle point. But yeah. So in principle, I don't know if for some k one eigenvalue is positive. And in fact, no. I don't always have Turing instability. Depends on many things.
But you know for sure that one is negative.
I know for sure that one is negative. Yes. So actually, I should have said it better. We know, because we have imposed it, that the determinant of the J0 is positive and the trace of J0 is negative. But this determinant of JK greater than 0 is something I'm imposing. So I know here I have lambda 1 and lambda 2 real part, negative. If for some k this is positive, for some k one of the two will be positive. So this will migrate to be positive. Okay. Thanks for the question. So now we can write explicitly. So lambda squared, here I have the trace. So it's fu plus gv minus k squared du plus dv lambda. And then plus the other term I need to look at it. So I have fu minus k squared du, fv minus k squared dv. Yes, and then I have minus fv and gu equals 0. So and I can rewrite this part. So I have a term in k to the 4. So I have du dv k to the 4th. Then I have a term in k squared du gv plus dv fu k squared, and then I have the plus the determinant of J0, because here I have, sorry, this is G, it's fu times gv, and then I have minus fv gu. So this is a polynomial of degree 2 in k squared. So now the expression, explicit expression for lambda 1, 2, okay, is the usual formula. But there is something interesting we can see from it. So lambda 1, 2. And then we have b, so the coefficient b of the parabola in lambda. So we have trace of J0, this one, minus k squared du dv. I will, delete this. Remember just that it's a polynomial of grade 2 in k squared. Then we have plus minus the square root of the same thing. So trace J0 minus k squared. All squared. And then I have minus 4h of k squared. So that should be correct. It's a bit tedious, but once in a lifetime, one should do it. And then, of course, close parentheses. So what can we see from here? So the first thing that I said before, that one eigenvalue is always negative, because the trace, we know it's negative. And here we have negative minus something positive. So this part is always negative. So it means that one root is always negative. Now, what is interesting, I think, is that now here we have something positive. So we are able to have one of the two roots positive only if for some case h is negative. This means that all the quantity under the square root needs to be positive, which means that if there is an instability, it's not oscillatory because there is no imaginary part. Okay? So if we imagine we have our system in the neighborhood of the equilibrium, we perturb, this is the UB. Okay, the trajectories, if they go away exponentially, of course, without oscillating. We can have oscillations, but towards the equilibrium. Because if there is an imaginary part, both roots are negative, and so we oscillate towards the equilibrium. Okay, we need at least 3 species to have what is called wave instability, or other additional hypotheses that we will see later on. Okay, so now we need to impose that this quantity is negative for some k, for some k squared. So I will rewrite the explicit form of the polynomial h of the parabola. So du dv k to the fourth minus du gv plus dv fu k to the fourth to the second plus determinant of j0. So I will not do all the calculations, so I can comment with an example, but I will just give you a trace on how to prove it. It's just algebraic calculations. Okay, so this is positive, the first term. So it's a parabola with positive concavity. So let's say we want to study h of k squared. Am I writing well enough? Nobody's complaining in the chat? Okay. K squared. K squared is positive, so we only have one axis. Okay. Determinant of j is positive, so we start from here. We need to have some case for which, so we know that it goes in this direction. We need to impose that there is an interval of k's that is negative. So to do this, we need to impose that the minimum of the parabola, so the minimum is minus b over 2a. Yes, so minus b over 2a, given a parabola a x squared plus bx plus c equals 0. Okay, and so we need that for this value is negative. So we have a certain k squared minimum that is equal to exactly minus b. So this coefficient is b, and we have du gv plus dv fu over 2 times a, so 2 du dv. This needs to be positive because it's k squared, cannot be negative. And so we already have the first condition. So the third, we have the trace of the J0, then determinant. This is the third condition. This to be positive. And now we need that h of k squared minimum, so with this value, this to be negative. And with some computations, you can try at home. I will give you the expression if I did all the calculations correctly. You should find the fourth condition, that is minus du gv plus dv fu square over 4 du dv, first term, and then plus the determinant of J0. This needs to be negative. Okay, so I'm almost done with what I wanted today. Maybe I will do the example Thursday. So the union of the conditions 1 and 2 that we saw before, they give the conditions for the homogeneous stable equilibrium. Conditions 3 and 4, plus 1 and 2, of course, they give that there are necessary and sufficient conditions for Turing instability. So if these conditions that depend on the diffusion coefficient of the species and on the model parameters are satisfied, we have Turing instability, meaning that perturbing a system in an homogeneous stable equilibrium, we have instability. Yeah?
This corresponds to these 2 points.
No. These two, if these two are verified, so if this is positive and this is negative, it means that there exists an interval of wave numbers for which this is, and we can see it with something that is called dispersion relation. That is probably the most important thing of today, that maybe I should have said a few minutes ago and not write on the photo finish.
Sorry, but when you have the negative H, you're going to be able to have the positive.
Yeah, exactly. So the interval is K1. So I don't know if online you heard what he said. So he said, if I have the negative H, then I have positive eigenvalues. Yes, that's exactly what we have. So now if we have the real part of lambda, so the eigenvalue of the matrix JK, function of K or K squared, doesn't really matter. We just know that on the x-axis we have K squared. So the system without space is on a stable equilibrium. So it means that this function starts negative. Okay. And then if this condition is satisfied, we have an interval of K for which this is positive, and those K's are the same. So the two critical K's are exactly the same. And this is called dispersion relation. If some of you know about synchronization dynamics, you may have heard of the master stability function. They're not exactly the same thing, because the master stability function is the maximum Lyapunov exponent as a function of the coupling. Here, at the end, it's not exactly the maximum Lyapunov exponent, because the maximum Lyapunov exponent is real. Here we need to impose that it's real. But then at the end, yeah, it is a master stability function. It means something more, because this K is the wave number. So it affects how the instability is dispersed, and so how the pattern is shaped. Okay, so there are two things left that I will do next time. I will start with that. Next time, I will show you that we need the inhibitor to diffuse faster than the activator. So dV has to be greater than du. And actually, in practice, has to be much faster than du. So Turing published his work in 1952, and experimental patterns were obtained more than 50 years later in Belgium. There's all a line of Belgian chemists, one of which Ilya Prigogine invented the model that I will tell you about next time. And so this condition is very, very strict, and it's in contrast with the abundance of pattern that we observe. So there are many ways of relaxing these conditions, adding physical assumptions. For example, we can add, as maybe we will see at the end, a finite propagation to the signal, because with the fixed equation, we have an instant propagation. We can add noise in the equation, because natural systems are intrinsically stochastic, chemical reactions, biochemical reaction, etc. Okay, and the good thing is that every time that we add physical hypotheses, it's easier to have patterns. So I like this because to me it means at least that it's a good theory. Okay. Okay, so yeah, thank you very much for your attention. Thank you, people online. Thank you. And if you have any question.
So some question from online, some question from here. You can open your microphone if you want. No? No? What was very clear.
Thank you.
Very good lecture. So this is why we don't have any extra, and we are very much looking forward for the next.
Thank you.
To know the follow-up of the story. So we will be back on Thursday, the same time, 1 o'clock here.
1 o'clock, not a bit.
Yes, well,
okay.
1 o'clock,
Okay.
because after the people.
Okay.
Roughly 1 o'clock, we have this breaking highs first. And then also the next week, we will have other 2 lectures. I just want to stress that this semester, we will have other 2 mini courses on networks. And so one is from Cíntia de Oliveira, and the other is from Lorenzo Giambagli from Florence. So it will be a very interesting semester once more. So thank you very much to everyone. Bye-bye.
Thank you. Bye.